Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, everyone. It's my pleasure to welcome Sovik Sen from Duke University. Sovik is graduating, and his research has been focusing on the 5-layer of wireless communication, both for improving the communication quality as well as using it as an interesting way to sense what's around the wireless devices. So today he will give a talk on his research, re-architecting wireless systems using 5-layer information. Thank you.
Thanks for the introduction, G. It's a pleasure to be here at Microsoft Research. As a student, I've seen so many things that have come out of Microsoft Research. It's an honor to be able to give a talk here. Thanks a lot. And I see that the weather is changing, and it's probably going to become worse. I hope that my talk is also not in that direction. So hopefully you will go out of my talk with a good feeling. Okay, so today I'm going to talk to you about how we can re-architect wireless systems using physical layer information. So wireless is becoming ubiquitous. If I say wireless, and if you go back 5 years ago, you'll probably think about your wireless router, or your laptop, which has a wireless interface, or your phone, which connects wirelessly. But now, if you look around, you see that so many of these devices are becoming wireless. And this includes your wireless speaker, your wireless mouse, your iPads and iPods, your wireless streaming device, for example, the Apple TV, your wireless car receivers, and we all are also seeing wireless coming to medical devices. So with all this, demand has skyrocketed. And we have seen a 25 times increase in wireless usage over the last 5 years. And Cisco is predicting that this explosion is going to continue. So from network service providers' perspective, outages have become a reality, and they are spending billions to solve this problem. We don't see unlimited data plans anymore as our good old days. Now these providers are trying to solve the data crunch problem. They're forcing us to pay per byte. FCC is trying to solve the problem. They're calling for better use of the available spectrum. So in other words, the problem is not of spectrum alone, but underutilization of the available spectrum is a major issue. And we as researchers have looked at this problem for quite some time. So if you look at our communication community, we have made significant leaps in achievable physical layer capacity by using techniques like MIMO, OFDM, coding, etc. And then if you look at our networking community, we have made advancements in distributed algorithms and protocols, scheduling, coordination, and things similar to that. But then, if you bring them together, this is what you get. The MAC layer or even the network layer throughput is only a fraction of the physical layer bitrate. Now, why is that the case? Particularly in case of wireless, because of the layering separation between the MAC and the physical layer, a lot of useful information is lost. So if you can co-design these two layers together, it's possible that this this lost information can help us in solving this challenge. Now, this is not a new observation. In fact, researchers have recognized the need to share information across layers. But this observation was instantiated mostly using simulation and thought experiments. There was no experimentation platform available, and hence it was difficult to build practical working systems and understands practical implications from this direction of research. Now, when I started my PhD 4 years ago, software radios were gaining popularity. And since then, they're changing the landscape of wireless systems. These devices essentially gives us a transparent physical layer and enables networking researchers like us to experiment in a more holistic manner. And recently we are seeing this trend to continue. Chipset designers like Intel and Atheros are giving us more and more wireless physical layer information to play with in the higher layers. So if you think about broadly, we as networking researchers, we have been working with abstractions, and we have treated the physical layer as a black box. And we have tried to design protocols and primitives around this black box. And we can go ahead and improve performance only to a certain extent if we work with a black box. At some point, we have to open this black box, look deeply, and come up with more subtle abstractions that can be used in the higher layers. These software radios gives us a transparent physical layer and enables that kind of experimentation in a holistic and sometimes in an unconventional manner. And our intention has been to contribute in this space. So in our research, we find that physical layer information and capabilities can be used to solve challenges in wireless networking. And these problems includes contention resolution, interference management, rate control, and enterprise networking. And as we are doing this research, we also find it interesting that physical layer can be viewed as a sensor, and the sensing information can be used in the application layer, helping emerging areas of mobile and pervasive computing. So in the later half of my talk, I'll talk about how we could use physical layer information to address challenges in indoor localization. Let me first start with wireless networking. At this point, I would like to state that we'll instantiate our ideas through Wi-Fi purely from a platform consideration, but some of the core ideas are generalizable to other wireless technologies. So let's start with a Wi-Fi functionality called distributed channel contention. Now, contention is a very general problem. It happens whenever there is a resource and multiple parties are interested in sharing or accessing that resource. In case of wireless, channel is a shared resource. Why? Let's think about that through this example. Let's say AP1 is your router at home who wants to talk to your laptop R1, and AP2 is your neighbor's router which wants to talk to its client R2. Now, since these two access points are nearby, they cannot talk simultaneously, because if they do, R1 will not be able to hear any of them. And this is analogous to two people talking together. If I am talking to you and someone else starts talking in the middle, you will probably not be able to understand any of us. Now, of course, you can control who talks when, but that is not possible in a distributed system like setting like Wi-Fi. So let's see what Wi-Fi does. Wi-Fi implements a scheme called randomized backoff. And the idea is that I'll select some random number and you will select some random number, and whoever has the lowest random number will win the contention. And let's see how that works in this example. Let's say AP1 has selected a random backoff value of 15, and AP2 has selected a random backoff value of 25. Now observe that these access points know what random numbers they have chosen, but at this point they do not know the random numbers of other access points. So to do that, Wi-Fi says, let these access points count down from the respective random numbers. And the idea is, whoever hits 0 first has the lowest random number, and hence he's the winner of the contention. So let's see how that works here. AP1 is going to count down from 15, and AP2 is going to count down from 25. AP1 has a lower number than AP2, and hence it will hit 0 before AP2. It will know that I'm the winner, and it will go ahead and transmit its packet. While AP1 was transmitting, AP2 will sense AP1's transmission and freeze its backoff value at 10. Now let's say AP1 has finished its transmission. It has maybe more packets to send to its client, so it will select a new backoff value. Let's say that is 18. AP2, on the other hand, will start from the previously frozen backoff value of 10. And in this instance, since AP2 has a lower backoff value, it will hit 0 before AP1. It will win the channel, go ahead and transmit its packet. Now this is great, and this is what is running in all our laptops now. But there is a problem. The problem is, during all those red intervals of Backoff, the channel has to remain idle. And that causes a considerable amount of channel overhead. And to give you some perspective of how much overhead we are talking about, at 54 Mbps, almost 1/3 of the time the channel has to remain idle due to Backoff. So if you look back in our community, we have been trying to solve this overhead from contention resolution for quite some time. And this goes back to 1971, where the first Aloha systems were first proposed. And still we see a lot of research to optimize the wastage from countdown. So we can think about contention estimation, where researchers have proposed that we can pick lower versus larger Backoff values depending on how many access points are there in the network. Now, contention is difficult to estimate, particularly in case of mobility. I might be here now, and I might go out in the next second, and whatever information you have regarding me and my traffic and topology might be stale. Of course, you can control who transmits when, but that requires synchronization, and it does not scale well in chaotic networks like Wi-Fi. So let's take a step back and think about what we are really trying to solve here. Backoff is not fundamentally a time domain operation. It's a concept which says that let people choose random numbers, and whoever has the lowest random number will win the contention. Now, Wi-Fi implements this concept in the time domain by counting down in time. Since time and frequency are interrelated, we ask the question, can we implement Backoff in the frequency domain? And if we can, are there any benefits in doing so? So we find a scope in current Wi-Fi physical layer which adopts OFDM. Now OFDM is a physical layer design in which the wideband channel is divided into 48 narrowband data subchannels called subcarriers. And this is done purely from a physical layer motivation because it copes better with fast frequency selective fading. We find a MAC opportunity here. We can pretend these OFDM subcarriers as integers, and I'll propose a system called Back2F, Backoff to frequency, which will try to emulate randomized Backoff in the frequency domain. So before I make you more confused with this complicated slide, let's move on to the key idea. Let's say, as before, AP1 wants to talk to R1 and AP2 wants to talk to R2. Like Wi-Fi, we'll let them select random numbers. So AP1 has selected a random Backoff value of 6, and AP2 has selected a random Backoff value of 34. Now Wi-Fi will make them count down from these numbers. Instead, we'll make them transmit these Backoff values on their corresponding subcarrier. So AP1 will transmit a signal on its 6th subcarrier because this Backoff value is 6. AP2 will transmit a signal on its 34th subcarrier because its Backoff value is 34. Now observe, yet these access points do not know what Backoff values other access points have chosen. That is why they cannot conclude whether they are the winner. To do that, we'll introduce a listen antenna. And let's focus on the listen antenna and think about what these access points will see at the listen antenna. So for AP1, it will see that 6 is active because AP1 itself is transmitting on 6. But apart from 6, it will also see that 34 is active because AP2 is transmitting on 34. AP2, on the other hand, will see a very analogous figure on its listen antenna. It will see 34, its own Backoff, is active. But apart from 34, 6 is also active, and that means some other access point have a lower Backoff value. And given that lower Backoff gets more priority, it will know that it has lost the contention. AP1, on the other hand, will look at his listen antenna and see that 6 is the lowest Backoff value it can find. That's the same as his own Backoff value, and hence it will know that it is the winner. It will go ahead and transmit its packet on all the 48 subcarriers by taking the entire band. Now observe that we have a difference with Wi-Fi here, and one of the differences is on your listen antenna. By looking at what you are seeing on the listen antenna, it is possible to know what Backoff values were chosen in the network. And can we leverage this further? We can, and let me show you through this example how. Let's say that a black access point is seeing these Backoff values on the listen antenna. So the red spike is its own Backoff number. It has chosen a Backoff value of 12, and the black spikes are Backoff values of other access points in its neighborhood. Now since active subcarriers imply Backoff chosen by other access points, by looking at this listen antenna, this access point will know what is its rank in a sequence. Since the red spike comes after two other spikes of other people, it will know that its rank is 3. And if other access points are seeing a very similar picture on the listen antenna, it's a global sequence, and hence this enables a back-to-back TDMA-like transmission. Now this sounds good, but is there a benefit from doing frequency domain Backoff versus time domain that is implemented in Wi-Fi? We believe this is because while conventional packet transmissions can take 250 microseconds, average temporal Backoff can take about 100 microseconds. Frequency Backoff will happen in orders of 1 OFDM symbol, which is 4 microseconds.
How do you handle a hidden terminal problem in your previous slide?
We don't. So Backoff has been designed for coordination. So if you think about Wi-Fi, backing off in the Wi-Fi, it was designed for coordination. It was not designed for hidden terminal. So we have not tried to solve the hidden terminal problem in this project. We have tried to solve the coordination problem in this project. We'll talk about how we can solve the hidden terminal problem in the next project I'll talk about today.
Excuse me.
Sure.
So how about the transmission from the mobile clients? You have these additional antenna too, right?
Say that again, sorry.
So you're assuming that AP is actually contending with each other and use an additional antenna for just listening for subcarriers. So if that happens on a mobile device, you also need another antenna, right?
Yes.
And this seems to be not very efficient use of the digital antenna as a resource, right, for both power and air time. So you can potentially use them for the MIMO and other multi-antenna techniques.
Yes. So we are actually complementary to MIMO. If there is a MIMO antenna, we should probably use our system more, because we are doing contention while there is no transmission going on. So if there is a second antenna, Backoff happens when there is no transmission. So you can use these two antennas intelligently to reduce the coordination overhead, and after you have won the contention, you can transmit just like MIMO transmitter transmits using both the antennas. So we are trying to use the MIMO antenna more intelligently. And what was your second question? Sorry.
That's just a question.
Okay. So, but this sounds too good, right? I mean, there should be some problems here. So, what are the side effects with this? And let's look at them. Firstly, will there be a lot of collisions with this scheme? And observe, this is a pertinent question because we have only 48 numbers to choose from, because there are 48 data subcarriers. If there are 50 access points who are choosing numbers from 1 to 48, there is a high probability that 2 of them will choose the same number, and hence both of them will think that they are the winner. They will cause a collision. For example, here the red and the green access point, they have both chosen a random number of 2. They do not know that some other access point is on that same subcarrier. They will go ahead and transmit in parallel, causing a collision. So to solve this problem, we always prescribe a second round. And the idea is the winners of the first round will come to the second round, and they will choose another set of random number. So the red and the green access points, who are the winner of the first round, came to the second round. They chose a number of 3 and 5, and depending on what numbers they choose will give them priorities. Now this will reduce collisions because the number of winners in the first round will be less, and hence the number of people who are contending in the second round will also be less. But there is still a problem. The problem is that if you have only a few access points in the second round, TDMA that we proposed earlier will not be effective. Why? Because the number of access points participating in the TDMA depends on the number of access points in the second round. If you have only 1 access point in the second round, that's no good because the TDMA size is essentially 1. You really want 5 or 6 of them in the second round so that they can all transmit back to back like TDMA without doing another round of backoff. So we optimize for TDMA also. Instead of the red and the green access point, we also bring the purple to the second round. And how do you do that? I'll skip in the interest of time, but this is done using local decision. These access points observe how many subcarriers are active and what kind of collision probability is fine for the network, and depending on that they decide whether they should come to the second round and peak backoff values. The idea is we want as many access points in the second round as possible, given that it does not cause a lot of collisions. So in the second round, by looking at the listen antenna, these access points will know their rank in the sequence, and this will enable a back-to-back TDMA-like transmission. For example, the red access point will know its rank is 2, it will wait for only 1 packet transmission, and then without doing another round of backoff, it will transmit its packet in a back-to-back fashion, saving channel airtime. So let's see how this compares with Wi-Fi. In case of Wi-Fi, we do 1 backoff per packet. So if you think about this sequence, purple is going to back off and then transmit, followed by red and then green. In case of back to F, we'll do 1 frequency backoff, followed by back-to-back packets in a TDMA-like fashion. And by cutting down all those red intervals of time domain backoff of Wi-Fi, we are trying to save channel airtime. Now whatever I've told you until now assumes that these access points, the purple, red and green, can hear each other, and they have a similar picture on the listen antenna. Now this is not the reality. In reality, you will have scattered access points and you will have multiple collision domains. I might be able to hear J and J might be able to hear Atul, but I may not be able to hear Atul. Okay. So this, I'm showing an example which is analogous to what happens. Let's say that the blue and the purple access points are in 1 collision domain. That means they can hear each other. And the purple, red and the green access points are in some other collision domain. They are able to hear them. But the blue and cannot hear the red or the green access points. Now let's say that these are the backoff values they have chosen. Okay. So if you look at them carefully, green, purple and blue's order are in sequence. Okay. Now let's think about what happens when green is transmitting. When green is transmitting, purple has to wait for green, but because it has a lower priority. But then blue has to also wait for purple to start and finish transmission. It has a lower priority than purple. It can only start transmission after purple has accessed the channel and transmitted. Now this is no good. If you are the blue access point, you will sit there, you will not see anything in the channel going on because you cannot hear green, and you will think, why am I not being able to transmit, although there is nothing going on? This is like a lost transmission opportunity for me. Yes?
I think it's more than that, right? So purple will believe it's number 2 through this green consensus, right? And the blue guy will believe it's also number 2 through that blue circle caucus, right? So the 2 of them were essentially transmitted at the same time.
So the ranking is relative, right? So purple knows both blue. So essentially blue doesn't know green, but it knows that its ranking is after purple.
But But I thought in the TMA mode, it says, I know my ranking is 2.
Right.
So I'm going to wait for a packet and transmit.
Yes, but you will not hear the green packet.
Right.
Because you are in a different
but
collision
then
zone.
when it transmit, purple is also transmitting, because purple also make a local decision. I'm number 2. I'm going to transmit it. I'm going to wait for a slot and transmit.
Right.
Well, the two of them will transmit at the same time?
No, unless both of you are hear the same packet. So in this example, for example, when green is transmitting, blue will not count that as one packet, right? Because blue cannot hear green. It only knows that purple is the one I should wait for. Purple's transmission is the one I should wait for, right? So purple, after purple starts and finishes transmission, then blue will go participate.
It only knows the time. It knows I'm the second one in line. It doesn't know the purple. It doesn't monitor the purple guy.
Yes, absolutely not. Yeah.
Right. But purple says I'm also the second guy in some other
ranking. Yes.
Right.
Yes.
And they will essentially transmit the same time.
No, because when purple is saying that he's the second guy, he's looking at someone else and hence saying that I'm the second guy, right? So that person will transmit. When that person is transmitting, blue will not count that. Okay. So after that, purple will transmit, and when purple is transmitting, then blue will know. Okay, so this is the first transmission that I was waiting for, and then blue will transmit. So this is an order that is happening implicitly.
Okay, we should probably take it offline, but I'll probably miss something in the
So, to pick up on this point, right, let's forget about the red one, and let's assume you only have the purple, the blue, and the green, right? Mm-hmm. So let's say the middle one becomes number 1, and then the other two guys assume that they're number 2 in the order, but they don't hear each other, so they don't know the number 2s.
Yes.
So number 1 transmits, and then both number 2s are going to go and transmit, right? At the same time.
Yeah, so that is true. That is true. And that is what the order says, right? Essentially, green knows that there is one person ahead of me, and that is purple. So after purple finishes, green will transmit. And the same thing will happen for blue also. Yes?
Right.
Depends on where the receivers are. So if the receivers are in a different place, if green receiver is here and blue's receiver is over there, it will not cause a collision. But if the receivers are in the middle, they will cause a collision. This is very similar to a hidden terminal collision. Yeah. So we are not solving the hidden terminal collision problem here. This Backoff is not designed to solve a hidden terminal collision. It is designed to solve the coordination problem. That is what we are trying to address. So we have the same problem as Wi-Fi has in terms of hidden terminals. Okay, so let me move on. So here we have a problem that blue will keep waiting for purple, and hence when green is transmitting, it will not transmit, and it will keep thinking that there is nothing going on in the channel. Why am I waiting for someone else? So observe, Wi-Fi does not have this problem. And what Wi-Fi does is, blue as a Wi-Fi access point will wait for purple for a while, and if it sees that purple is not transmitting, it will keep counting down and it will go ahead and transmit its packet. So our back-to-F solution is to emulate Wi-Fi. And let me show you through this chart here how we do that. So let's say initially everyone does a frequency Backoff and they have these Backoff values. If I'm participating in that Backoff and if I'm the winner, it's my turn, I can go ahead and transmit. After the transmission, I'll pick a new Backoff value if I have more packets to send. Now, if I'm not the winner, and if I'm waiting for someone else to transmit, I will sense the channel for a while. I will listen for that person to transmit, and if I see that that person is not transmitting, I can go ahead and transmit my packet. Now, let's see how that works in this example. Initially, green is the winner, and hence it will transmit. While green is transmitting, blue will wait for purple, will listen for a while. It will see that the purple is not transmitting. It will lock off from this Backoff, will do its own frequency Backoff, and if it will see that the channel is still idle, it will go ahead and transmit. Now, after green has finished its transmission, observe that red is waiting for purple. but red cannot sense blue. So red will also listen for a while for purple to transmit. Purple will not transmit because it is waiting for blue to finish, and hence red will do its own backoff and go ahead and transmit, and this will be followed by purple's transmission. Now the thing to note here is that if you look at the sequence of backoff values, that sequence and the way it was executed are different, and this is the same sequence that will happen in case of Wi-Fi. We are trying to do the same exact thing. We are trying to imitate Wi-Fi here, but we are also trying to cut down on all those red intervals of backoff wastage that Wi-Fi has. So given that I have explained to you our key ideas, let's move on to performance evaluation. There are two key questions that we need to answer here. First, can Back2F detect subcarriers reliably? Because if we cannot, then it's not possible to know what backoff value other access points have chosen. The schedule will be all wrong, and hence we might have a lot of collisions. And second, if we can detect subcarriers reliably and do frequency backoff, how much throughput gain can we have over Wi-Fi? So to answer the first question, we did an evaluation on ESRP based testbed, and to answer the second question, we evaluated using laptops and access points at 65 locations. So let's try to answer the first question. Observe there is a practical challenge here. If I am an access point and I am transmitting my backoff value on my transmit antenna, since my listen antenna is also on me, there will be a high self signal from the transmit to the listen antenna. And because of that, it may not be possible to understand who else is transmitting on the listen antenna. And let me show you through this example how that happens. So here I am showing you a frequency spectrum on the listen antenna. So I, as an access point, I am transmitting on a subcarrier of number 45. So that is why you see a high self signal on 45. Now there are other access points who are transmitting on subcarriers between 40 and 60. And from this figure, it's not possible to say what particular subcarrier values they have chosen. You know that there are people who are between 40 and 60, but you cannot really tell what numbers they have chosen. And this happens because the self signal from 45 overflows into the adjacent subcarrier. Now to solve this problem, Wi-Fi uses 64-point FFT to get a frequency spectrum at any receiver. We find that if we use a higher point FFT, it's possible to resolve these frequencies better, and hence from this diagram you can see that although the self signal is high, we can clearly see where the other peaks are, and from there find out what subcarriers are active and hence what backoff values other people have chosen in the network. So using this, I present here our subcarrier detection performance. So here on the y-axis, I'm showing you detection accuracy as I increase the distance in subcarriers from the self subcarrier on the x-axis. Essentially, the first point on the x-axis is most vulnerable to the self signal. And to help you read this graph better, we have a robust subcarrier detection at 14 dB. And what is this 14 dB? This 14 dB is essentially the signal strength of a weak access point at my listen antenna while my transmit antenna is busy transmitting my own backoff value. So if we can detect subcarriers, how much throughput gain can we have over Wi-Fi? So here I'm showing you on the y-axis throughput gain over Wi-Fi as I increase the number of access points on the x-axis. And as you can see that we have higher gain at higher rates. And why is that the case? In case of Wi-Fi, the overhead due to backoff is like a fixed cost. If you increase the rate, the amount of airtime you will take for the packet will reduce. But the overhead cost is fixed, and hence the backoff overhead is higher relatively at a higher rate. We are trying to reduce that backoff overhead, and hence we have a higher gain at higher rates. Yes? Sorry?
Is there only downstream traffic in this experiment, or clients are also sending?
In this experiment, this is in this particular graph, exactly this graph, this is the upload traffic.
Upload traffic.
Yes. Yes.
Okay,
This particular
so I
graph.
thought, since your description was all in terms of APs, I thought like it's only APs that are doing back to that.
Right. So both the clients and the access points can do back to web. That is
So you are assuming that clients have a secondary antenna.
yes.
And in that case, what is the downside of using the 256.FFT?
So the downsides of there is a trade-off. Good thing about using back-to-web is that you save sensing energy. Essentially, when you are trying to sense and find out whether the channel is idle or not, right? So you save some energy there, but you also spend that energy on using that higher point FFT. So it's I do not have a good answer of whether that energy trade-off how it will play off.
You haven't done measurements with how much higher energy consumption happens with the 256.FFT?
Since you know what you're sending, can you just use apply those cancellation?
Sorry, I did not.
Can you just do some kind of cancellation of the listen antenna because you know what you're transmitting and the
Right. Right. Yeah, so we can definitely do that, but that adds some more complexity to the system. So we started off not by thinking how can we do this without cancelling. And apart from cancellation, Ratul, to answer your question further, you can use the system without using 256.FFT also. So if you just use 64.FFT, you can use every fourth subcarrier, and that will give you a very similar performance in terms of subcarrier detection, but then you have lower number of numbers to choose from. So you may increase collision, but that is possible to resolve by increase the number of rounds we are doing.
So, does 256 means that you are sampling the channel more frequently, or is it just you are doing more calculations?
So we are taking more time.
Time to complete,
Yes.
or are you sampling at a higher frequency?
No, you're just taking more time.
So adding a second antenna and doing the sampling on the subcarriers as well, that has to be in a continuous manner, I guess, right?
Sorry, I could not
So
hear.
you're adding a second antenna and you're continuously sampling, like receiving on the second antenna too, right?
Right.
The subcarriers. And you also have to do some sort of backoff there when needed, so it can continue on listening. How do you quantify the energy impact of that?
No. So, but to answer your question, you need to activate the second antenna when you are transmitting on the first antenna your backoff. So, if you are not in the backoff round, we need not turn on the second antenna. So only when you are doing the backoff, you need to turn on the listen antenna or the second antenna.
To get this plot.
Sure.
Did you actually have 50 quote-unquote access points with both two antennas and generate these from?
No. So this is not a test bed result. This is a trace based result. So we didn't have 50 nodes talking to each other. We don't have that. We didn't have that much resource.
Simulated results.
This is not simulated, but it's trace based. So essentially we went and took measurements in different for different links, and we characterized what the interferences are. We characterized what the subcarrier detection capabilities are from our ESRP, and we used all that information to find out what the gains can be.
But just following up on that, like the level of detail that went into this experiment. So your antennas now require like a quicker, it seems, like transmit, receive, turnaround.
So we have not so as a negative in our case, we have not implemented that system, but we are taking care of the fact that the turnaround time is what the turnaround time of typical hardware is. So essentially, if you think about SIF duration, that when you send a packet and then you have to send an ACK within 9 microseconds, right? So we are taking care of the fact that you need 9 microseconds for sensing and turning around from the receive to the transmit mode. So all this information has gone in this plot.
I see. So, but the system was not implemented. Is that what you just said?
That my 9 microsecond system was not implemented.
So what was implemented?
So the subcarrier detection is happening on the USRPs. Collision detection is happening on software radios. All the traces are real traces. So we went around and find out links. So essentially we transmit on links and found out what the interference how two links interfere. So we took all the data and from there we did this trace-based throughput evaluation. So the previous graph was a test-based graph. This graph is a trace-based graph.
So and this was like you basically took like just measured the Wi-Fi environment and you.
Yes.
And then.
Yes. Yes.
And you had 50 active clients in your traces.
No. So as I was saying that we don't have 50 nodes. So we took links. So essentially there are 50. So we took one client, one access point, and from there we took the for that link, what is the rate, what amount of interference that link is going to have from all other links that is there in the interference. So we measured that as well, and we throw all this information to the trace-based emulator.
This is simulation based.
Sorry.
This is basically simulation based on real parameters that you extracted from data.
Yes. Yes. But there are parameters that goes in from the real world, as in how much can you detect from the subcarrier, what is the real interference level, what is the real rate that is supported in the links and things like that. So we could not essentially the software radio based systems it's hard to do a quick turnaround of 9 microseconds. So that is why it's hard to build a real system and take evaluation results here. We actually have done that, but the turnaround time is such that it's hard to compare with Wi-Fi, which requires a quick turnaround. So we have built the system, but to show the results along with Wi-Fi, we did this trace-based emulation.
So in your experiment, in the trace you collected, do you have the APs in the same contention domain?
Sorry, I cannot hear you.
So do you have 50 APs in the same contention domain in the trace that you collected?
In this graph, yes, but we have done, so there are other graphs in the paper which have looked at multiple collision domains. What happens? So there are essentially as I was saying, there are 65 locations at which we collected all this data, and from that spans the entire building. So that is why for those we have multiple collision domains and real traffic.
I'm still trying to understand. So you have a spot in Duke that have 50. You can have 50 APs.
So imagine this graph is wrong. Imagine the x-axis says number of clients and not number of access points. Okay, and imagine all these clients are trying to send information to the access point. So and imagine the fact that they are in a one collision domain. The single collision domain. So they can hear.
Setup you collect the trace. Is that the setup you collect the trace having?
For this graph,
clients?
yes. For this particular graph, I'm showing you yes, not in general.
What kind of traffic pattern did you assume for generating this graph?
So this particular graph was constant bit rate. Essentially,
So every client is trying to transmit
to
the next
access.
time.
Yes.
But since the backoff overhead is highly dependent on the traffic pattern of the transmitter. So if you have intermittent or periodic traffic, it's highly mitigated. And
so whenever, of course, I mean any amount of throughput gain you have, or you can show, depends on what kind of traffic you have.
So this is basically like an upper bound.
Right. So this is basically showing that how much throughput gain can you have when everyone is trying to transmit. But this also shows that when you're transmitting a packet, how much of channel usage are you going to improve by using back-to-F? Okay, so to summarize back-to-F, contention resolution is a very general problem. So I was saying it happens whenever there is a single resource and multiple parties are trying to access that resource. In case of wireless, channel is a shared resource, and we have seen several proposals who have tried to optimize the wireless channel access overhead. They have tried to optimize the time domain backoff operation of Wi-Fi. Now, backoff we find is not fundamentally a time domain operation. It's a concept which says that people will choose random numbers, and whoever has the lowest random number can transmit. Back-to-F shows the feasibility in the frequency domain, and it tries to alleviate the long-standing overheads of backoff. So let's take a step back at this point. We started off to reduce the gap between MAC layer throughput and physical layer bitrate. And we found that if we can solve the challenges in contention resolution, this gap can reduce. Now other problems that we can solve to reduce that gap further, wireless collisions is one such problem. Why? Because while there is a collision, the physical layer is transmitting at the best bit rate possible, but at the MAC layer your packet is corrupted and hence your effective throughput is 0, contributing to that gap. Let's look at the anatomy of a wireless collision, how it happens when it happens. Let's say T1 and T2, these two laptops, are associated with the access point R, and they want to talk to R. Let's look at a sequence of transmissions with time on the vertical axis. T1 wants to talk to R, and let's say it starts talking to R. T2 cannot hear T1. It also decides to talk to R. It starts in the middle of T1's transmission, causing a collision at R. Now T1 knows nothing about this collision. It will keep transmitting, and after the packet is the transmission is over, it will wait for an acknowledgement from R. Now of course, R is not going to send this acknowledgement because the packet did not go through, and hence T1 will keep waiting until the ACK timeout, and beyond that it will know that the packet did not go through, and hence it will retransmit the entire packet. Now we believe that this is not efficient. It would have been better if T1 aborts right after the collision. Why? Because there might be some other transmitter T3 who was waiting for T1 to finish his transmission, and if T1 aborts his transmission in the middle of the packet, T3 can come in and transmit to some other access point, replacing the fruitless transmission from T1. Now if you think about a more matured physical layer like the wired networks, this is exactly what happens. The transmitter senses the channel as it is transmitting. If what it senses and what is transmitting is not the same, it says that there is probably a collision at the receiver. It goes ahead and aborts its transmission. Now this is called collision detection, or CSMS-ED. And we have believed as wireless researchers that this is not feasible to do in the context of wireless networks. Now observe that collision detection is like prevention. Prevention is hard to do in the context of wireless, and hence we as wireless researchers have tried to cure collisions, essentially try to do something about the collision after it has happened. Now we try to break off from the convention and ask the question, can we imitate CSMS-ED or collision prevention in the context of wireless networks? So in the next few slides I'll talk about a system called CSMS-EN, which will try to achieve collision prevention in the context of wireless networks. And let me do that using this example. Let's say that the transmitter TX wants to talk to the receiver RX, and I'll call the data transmission signal S1. Of course, the collision happens at the receiver, and hence the receiver needs to detect it. Now let's say a collision has happened at the receiver. The transmitter is a wireless transmitter, and hence it has no idea about this collision. So the receiver has to send some feedback to the transmitter. We'll call this collision notification signal S2. Now observe, this is not enough yet, because the transmitter's transmit antenna is busy transmitting the data transmission signal, and hence it will not be able to find the collision notification signal. So to do that, we'll introduce a listen antenna. Now at the listen antenna, the transmitter can find the notification and can go ahead and abort the transmission, preventing the collision. This sounds good, right? But it does not work. Why? Because there is a high self signal between the transmit to the listen antenna. And because of this strong self signal, S1 is going to be so high at your listen antenna that in presence of S1, it will not be able to, it's going to be hard to understand the presence of S2. So when we face this problem, we didn't find anything that we can borrow from related work. And hence we started doing a lot of experiments on our ESRP testbed. And the observation we had is that if we can suppress S1 at the listen antenna somehow, we'll be able to detect the collision notification, or S2. And the idea we had is that S1 need not be an unknown signal. We can very well send S1 from the transmit antenna over to the listen antenna over wire, and because if we can do that, if S1 can become known, it is possible for us to suppress S1. Now in this setting, let's think about what we have at the listen antenna. At the listen antenna we have two signals, one over wireless, which has the transmit signal as well as the collision notification signal, and one over wire, which has the transmit signal only. So if you subtract, of course you will get S2, but then you will also get a lot of noise. Why? Because the S1's copy over wire is only an approximate of the wireless copy, because wire and wireless propagation is not the same. So because of this noise, it will become very hard to decode S2. Now when we faced this problem, we had an idea. And the idea was S2 need not be an unknown signal for this transmitter. The receiver can very well send its MAC ID as the collision notification, and because the transmitter knows its MAC ID, it need not decode for it, it can correlate. A correlation is essentially a mathematical operation in which it's possible to detect the presence of a known signal S2 in presence of even a high background signal S1. So if the transmitter is correlating for the collision notification, if there is any, it will have a correlation spike. It will know that there is a notification, it will abort the transmission, preventing the collision. So let's see how much throughput gain can we have by preventing collisions in our network. So to do that, we had a 10-node ESRP testbed deployed at Duke, and we found that across topologies, on average, we had a 40% gain in throughput over Wi-Fi, and this was particularly by preventing collisions. Of course, this number 40% will depend on traffic and topology, but CSMSCN essentially reduces the cost of collisions. And this enables networking researchers like us to be more aggressive in our protocol designs, not consider collisions as a big problem to that extent.
What was the traffic?
So
you should get this 40% based on what traffic, like what was the popping?
So this was a ESRP testbed. The traffic was a constant bitrate traffic, and the topology was essentially nodes trying to talk to each other across the geographical setting. So there was no particular setting. We just distributed nodes around. And essentially the CDF here, each dot corresponds to each link we had in the topology.
So what is the Ethernet level like?
So this is essentially like Wi-Fi. So whatever Wi-Fi does is essentially like Wi-Fi.
With capture?
Without capture.
Without capture?
Yes.
But as I understand, USRP can't really do the carousels.
So say that again. Sorry.
USRP, you can't really do. It doesn't. It's very hard to have a full-fledged implementation of Wi-Fi MAC, right? So which part did you implement in this?
So this particular system, as I was saying, like the previous system, we have implemented everything that we talked about, but it's all scaled down in terms of time. Essentially, the problem with carrier sensing on ESRP, or the problem of doing real-time things on ESRP, is that the turnaround times are big. So you cannot do 9 microseconds, but it's possible for you to do 900 microseconds. So essentially, that is what we did.
Are all the factors the same when you make this comparison? Your power output, your sensitivity, your gain of your antennas, are those all the same when
Yes.
you make this comparison?
Yes.
Okay.
I'm curious what you do on the receiver side to detect collision.
we don't attempt to do that. So essentially, if your client does not have a second antenna, are you asking that what do you do?
The receiving side. How do you know that two guys are transmitting together?
Right. So essentially, by looking at the physical layer properties, you can know. So the one we looked at specifically is essentially symbol level, constellation symbol level property. So, and to give you a very brief overview of that, if you think about constellation level dispersion, it accounts for both fading and interference. So if you look at fading, there is one property that holds for dispersion. Now, as you are receiving a packet, if there is an interference in the middle of the packet, you will see that the dispersion property or the dispersion distribution suddenly changes over the entire band. And from there, it is possible to know that there is an interference or there is a collision happening. Okay, so with this, let me summarize CSMSEN. CSMSEN tries to imitate collision detection or prevention in the context of wireless networks. So if you think about wireless researchers, we have tried to cure collisions before. Essentially try to do something to recover after the collision has happened. We believe that prevention is better than cure, and CSMSEN we believe is a first step towards this direction. So with this, let me summarize the wireless portion of my talk.
Can you place this stuff in context of the full duplex stuff coming out of MIT and Stanford?
Right. So two things. One is this was done before the full duplex.
Yeah, I meant more of a technical, like what are the key differences?
So if we have full duplex today, it will be more useful. But the key idea that is key in this project is correlation. Essentially, if you have full duplex and if you are trying to decode for a collision notification in band, that's going to be less robust than if you can do correlation, because correlation is more robust to another signal going in band. So
but what would be simpler in the sense, like, I mean, yes, correlation is easier, but correlation also carries less information than decoding does.
Right, but in this case, you just need one bit of information. You just need the information whether the receiver is being able to receive the packet or not.
But is the circuitry simpler?
The correlation circuitry is already there in a Wi-Fi receiver, because you have to correlate to receive the preamble or to understand whether there is a beginning of the packet. So the correlation circuitry is already there in a Wi-Fi chip.
It's already there, but is it simpler than decoding circuitry? Like, can you have like a cheaper collision notification system?
Yes, absolutely. Correlation circuitry will require much less of digital systems than a full decoding circuitry. Yeah, because you can do correlation at a signal level, and you don't have to do the other things that you would need to do beyond just the signal, like demodulation, decoding, and things like that to do the actual decoding or to get bits out of it. Okay, so with this, let me summarize the wireless portion of my talk. We find that physical layer information and capabilities can be used to solve the challenges in wireless networking. And if you can do that, we can reduce the gap between MAC layer throughput and physical layer bitrate. So beyond wireless capacity, can physical layer information still be useful? And as we are doing this research, we found it very interesting that the answer is yes. Wireless physical layer can be viewed as a sensor. And if you can use this sensing information in the application layer, it will aid emerging areas like mobile and pervasive computing. So now I'll talk about how we could use this sensing information from the physical layer to help indoor localization. So indoors, we see something called multipath. Essentially, whenever a wireless transmitter broadcasts a signal, it transmits the signal in all directions. So before the signals arrive at the receiver, the signals gets reflected by your doors, windows, and walls before coming to the receiver. And these reflections affect a physical layer parameter called channel frequency response. Now, since the channel frequency response essentially depends on these reflections, if you go and measure the channel frequency response in some other location, you will find that these responses are different essentially because the reflections are different. So if these responses are different in different location, that's good news in terms of localization, because it's possible to use these responses for location signatures. I can go and measure these responses around this building and create a database, and later when you go and give me a response, I can map in the database and tell you where you are. But even before I can do that, what is the stability of this response in a particular location?
Is there just one transmitter?
What is that? Sorry.
I mean, how many transmitters are there? Just one?
Yeah. So it's possible to do with one transmitter. More transmitter means more information, and hence you can do localization better.
The channel frequency response is location specific.
Right.
It's location, transmitter specific, right?
Yes.
Okay.
Yes. So even before we can do that, what is the stability of this signature or of this channel responses? Right? Because this might vary over time. This frequency responses at a given location may vary over time. But what we really need is to find a detectable pattern from which we can extract a location signature. So to understand that, we tried to do a lot of experiments using Intel 5300 cards. And we find that at a single location, in many cases, these responses are clustered, as I'm showing you in the figure here. So there are 20,000 responses in this figure, but as you can see, they're very much clustered. Now, of course, it is not necessary that you will have only one cluster in one location. In the same location here, in a later time, you can see another cluster. Okay. Now, if you look at these responses, observe that they have both amplitude and phase, because they're essentially complex numbers. If you take one subcarrier from that and you plot them on the complex plane, this is what you get. We observed that these clusters are essentially Gaussians, and by looking at these Gaussians, they have a mean and a variance, and this cluster mean and variance can be used as location signatures. But this can be only done if you have only a few clusters, because if there are a lot of clusters, it will be hard to identify all of them and create the database. So to understand that, we did measurements at. No, so that's what I want to talk about right now. So to understand that, we did measurements over a week at 30 locations, and I'm showing you a CDF of number of clusters we could find at these 30 locations. And as you can see, that most of these locations has a few clusters up to 5, but then there are some locations which has a lot of clusters up to 19, and this may mean that at these locations it is not possible to use these clusters as location signatures. So to understand that more, we ask the question, do all these 19 clusters occur with the same frequency? And we did measurements, and we found that it's not. Rather, if we take only a few dominant clusters, these clusters are dominating so much that you only need to understand or learn these few clusters, and these other clusters can be treated essentially as noise, and you need not learn all of them. So, yeah.
Did your experiments include humans?
Sorry.
Were there any humans?
Yes. I mean, this 1 week trace essentially was taken at a Duke engineering building where there are classrooms and people are coming along. Yes. We let them run continuously. It was a natural environment where human moves. So essentially, if you can learn these 4 clusters and you can build a map of it, it's possible to provide locations. Now I'll skip the technical details, but I would like to say that our system Pinlock could pinpoint paintings at the Duke Museum with 90% accuracy. Now, while we did that, we were very excited about this project, and we thought that this might be one of the ways to solve the challenges in pervasive localization. So we started talking to a lot of consumers of this technology, the Duke Museum of course, but also to a Walmart. And Walmart came back and said that this is not the need. Essentially what the need is anytime, anywhere localization. Now the problem with Pinlock is that we need to do word driving. You have to go and measure these responses, these clusters, before you can even give a location service. Walmart or consumers in that space are not willing to do that. So we took that learning and we came back and we asked the question, how can we design an indoor localization system without doing any watt driving? So I'll do the same here, but before I move on, I would like to say that please remember that these pin lock spots or the pin lock locations can be used as landmarks. Essentially, if you go there and if you give me your Wi-Fi signatures, I can tell you exactly where you are. Yes, Ratul.
Something about the channel frequency response. So is it consistent across hardware? Like if I watt drive with your card and then like do the oscilloscope differences, or they matter or not?
So it's hard to guess. So we used 4 cards, but it was the same vendor because Intel 5300 was the only card we could find which was giving this kind of information. So across vendors, if the antenna design is different, it probably might be different. But that is also it is possible that is easy to model, and there are some recent works which shows that is possible. So I don't know. There's some I have not a good answer there, but there are some recent papers which shows that if you have one card versus the other card, it's possible to model how this frequency responses will look at a different card, given you know what the response is at one card. Yeah. So you have to model the difference, and if that is possible, then that what you are asking is can be easy. Okay, so let's move on. So we asked the question, how do we design a truly unsupervised indoor localization system? And we thought that maybe we can borrow from outdoor localization, because outdoor localization has been very mature. If you think about outdoor location-based applications, you see several of them in the iPhone app stores and the Android marketplace. So as we were skimming over outdoor location-based applications, one technique that we found interesting is called dead reckoning. And I would like to go through you using this slide how dead reckoning can be used to provide location in an outdoor setting. So let's say you are that user and you go over the Microsoft building in this U shape. Now I can track your location by using the accelerometer and compass on the phone, because accelerometer will give me your displacement and compass will give me your direction. Now of course these sensors are noisy, and hence my estimated walking trail of you will not be the same as the ground truth. It will deviate away over time. But then outdoors we have GPS, and it's possible for us to correct these walking trails at this known GPS location. Let's see how. Let's say we started from almost the same starting point. We walked a bit, we consulted GPS and found the actual ground truth location, and we corrected the dead reckoning error. We did the same at a later point, and if you keep doing that, observe that the corrected dead reckoned walking trail is similar to the ground truth. So observe that these known GPS locations are like landmarks. So outdoors, in a nutshell, it is possible to dead reckon to find the location and correct this dead reckoning error at landmarks. So we thought maybe we can bring this technology indoors. Accelerometer and compass and orientation sensors work reasonably indoors, but GPS does not work. But observe, all we need are a few landmarks, essentially locations which have something unique about them, so that whenever you go at this location, we know exactly where you are. Pin lock locations are like landmarks, because whenever you are at a pin lock location, by looking at your Wi-Fi, I can say exactly where you are, and that's like a landmark. But Wi-Fi is only one sensor on the phone. If you think about all the sensors that are there on the phone, it might be possible to come up with more landmarks, essentially locations which have a unique sensor fingerprint. And as we kept thinking, our intuition said that is possible because of the inherent diversity in the way people move and the buildings are structured. And I would like to share you some of the ideas here. If you look at accelerometer, if you think about elevator, we find that there is this complementary bumps in the accelerometer space, and this happens due to the start and the stop of the elevator. whenever you go up the staircase, the magnitude of the acceleration has a high variance. If you think about sound, whenever you're at a drinking fountain or you're taking coffee from a coffee machine at a cafe, you see that there is a unique sound signature that shows up. And also we can find landmarks in sensor domains that we cannot perceive as humans. For example, magnetometer. So this is a lab at Duke. This is a computer lab, and essentially these computers are electrical devices, and they affect the Earth's magnetic field. So whenever you go and stand at the door of this particular lab, you will see that a unique magnetic signature shows up. And if you can learn that, you can use this as a signature. And we find that even no sensor reading is good for us. So this is a basement at our engineering building, and it looks very creepy. So even more creepy is that if there is one location in this basement where if you go and stand, you will not get any kind of wireless signal. No Wi-Fi, no 3G, forget 4G, nothing. So if you are trying to find someone and you know that person is in the building and you are not being able to connect to him wirelessly anyhow, there is a notion that goes around in our lab is that either he is with Romit talking to him or he is at that location. So essentially what I am trying to say is that even no sensor reading can be a signature. And if you keep thinking, there can be several that we can come up with. But the hard question is, how do we locate these landmarks or these locations with unique signatures without doing any warp driving? And we try to do that by using dead reckoning from outdoor localization. And let me go through this example and discuss how. Let's say in this building map, there is a computer lab, and it causes some unique magnetic fingerprint at that location, at the door of the building. So I will dead reckon you from the door of the building, one known location. So whenever you go there, and if you are giving your sensing information to the cloud will know that you are at a unique location, because whatever you are seeing on your phone is very different from other location that you are sensing. The cloud will not know where this location is, but the cloud will know your dead record estimate. So when I go there, the cloud will know that both of us are at the same location because we are seeing the same sensing signature, but the cloud doesn't yet know where the landmark is. It knows only our dead record estimate. As more and more people goes there, the cloud will have a better confidence about this particular landmark. It will still not know where the landmark is. It has its dead record estimate. Now, this dead record estimate can be independent because all these people, they might approach a particular landmark from different directions, and the sensor noise can be independent. And by law of large numbers, the cloud can take the centroid as the dead record estimate to find where the landmark is. So in our experiments, we find that within 2 man-hours, our landmark location error was within a meter. So if we can find these landmarks, it's possible to dead reckon and provide localization service indoors. So in a nutshell, we took a recursive approach. Initially, we knew only one landmark. That's the door of the building. So if you want your location, I'll give you your location by using dead reckoning using that existing one landmark. And of course, the localization error initially will be very high. But then I'm going to use all the sensing information from your phone as well as others. If it's possible to find a unique sensor fingerprint, we'll find the landmark location using the dead reckon estimates. And if you find a landmark, we'll add it to the landmark list. Over time, as more people goes in, you will see that more landmarks will come up in geography, and the landmark localization error will improve. As landmark localization error improves, dead reckoning will also improve, and then as dead reckoning improves, the landmark localization error will also improve in a recursive loop. So in the steady state, we expect to see that the localization error will go down. So to understand that, we did experiments in our Duke University and also a shopping mall, and we found that the localization error reduces over time as more of these landmarks are identified and the localization error of these landmarks go down. And in the steady state after 2 hours, the mean localization error was 1.63 meters. So to summarize the localization portion of my talk, yes?
Let me understand, why is this better than word driving?
It's
like with the systematic word driving, like I can just do it once or do it once a year or something and forget about it. Like this system now, I have no idea what it's going to do. And how much time it's going to take to actually give me the right result.
So,
and there are issues around error propagation as well. If two locations end up having the same signature, I don't know how dead reckoning is going to behave, because you're going to just keep propagating the error in a convoluted manner.
So let's take your comments one by one.
Yeah.
If you think about word driving, it's hard to imagine a system whether you will do only once a year. You have to do it periodically if the environment changes, right? So if you just think about this system, uses some component of word driving. Let's say you are doing Wi-Fi word driving based localization. This system will automatically learn that. It will know that this landmark was here today, and if the landmark goes away tomorrow, it can understand that. So it will automatically learn that. Also, to answer your second question about whether the errors will propagate. Sorry, can you ask that again?
It seems you're assuming a lot about the nature of the error once you're doing this unsupervised learning that you are doing. One is like, initially you may not even know if a location has unique signature. You may not just have,
right.
You just, it's just data coming in.
Right.
And two locations could have the same signature, or the signature of a location may not be unique by itself, depending on computers were on or off, for instance, in the lab. And so it's unclear to me how you're actually, first of all, like dealing with those issues, and the other is, I think by necessary you described the high level. But in the end, like it's hard to understand what happens with the system long term because of possibilities like that. Okay. So, and not to mention the uncertainty of knowing when the system is actually properly trained.
Right. Right. Yeah. So it's hard to understand. So if you look at the system and if you take a snapshot of the system, it's hard to understand whether the system has converged or not. That is true, because you don't have the information that where the landmark actually should be. Now, essentially, you are taking a multidimensional approach, right? If two locations has a very similar landmark fingerprint, it's possible that these two locations have a different Wi-Fi signature. So if you add Wi-Fi along with that, they will be different.
Well, now that's a contradiction right there, right? Like I said, two locations have the same signature. You're saying they're not. That's not the case I'm worrying about.
Right. Now, if within the Wi-Fi, within one Wi-Fi area, if two locations have the same signature, we will not use them because it's ambiguous.
But you don't know there are two locations.
We do not know there are two locations unless in geography the dead reckon estimates are giving two different clusters. See, if the locations are so nearby that these dead reckon estimates are giving you one big cluster, we'll not know that. But if the dead reckon estimates are such that there are two different clusters, we'll know that these are two different locations, and we'll not use the landmark at that particular instance at that point because that is ambiguous. You see that, and the good thing that I like about the system is that, see, essentially you are trying to find a few landmarks where you can correct the error, right? If your dead reckoning is good enough, you essentially just need some few landmarks, and
it's not just that. I think you are also, by taking the centroid for instance, you are assuming something about the nature of the dead reckoning error being completely unbiased, and I'll be surprised, I think, because the way structured vein buildings are laid out, that dead reckoning actually gives you a zero bias, by that I mean like that it's equally likely to be anywhere at the 10 answers it gives you. My intuition would be that dead reckoning is systematically wrong.
Okay.
Because people walk around certain paths in the building, it's not like it's not completely random.
So the error might be unbiased because the error is essentially coming from the sensor error. The sensors are unbiased, because if I take my phone and you take your phone, and we calculate the dead reckoning somehow using some algorithm, because our sensors are unbiased, you will see the dead reckoning may also be unbiased. So even if you walk at a location, if I and you walk at a location from the same exact direction using the same exact path, the dead reckoning estimate that the cloud will compute or the server will compute will be different because the sensors are different. The sensors are unbiased.
Have you done that micro benchmark analysis of dead reckoning actually giving you completely unbiased errors around the location?
We have not dig deep in it, but we have taken snapshots and we have tried to convince ourselves whether they are unbiased, and it seemed to us that it was unbiased.
By just looking at that.
Yes.
So in your dead reckoning, so you have the displacement from the sensor, and also you have the turn information. So in between turns, do you assume you're following a straight line?
No. We look at the accelerometer and the compass and gyroscope to dead reckoning. So
in between turns.
In between turns also. So
if the path is a little curvy.
Yes, it will. We'll account for that. We are not assuming that all the paths are straight or 90 degrees necessarily. Okay, so to summarize the localization portion of my talk, Wi-Fi fingerprints is a well-researched area in indoor localization. So if you look at the other sensors, there are also fingerprints in these phone sensors that we have. If you can bring them together, it is probably possible for us to help solve the problem of indoor localization. We try to do that, and we try to solve the problem of war driving by bringing dead reckoning from outdoor localization. So with this, let me summarize my talk. In my PhD, I try to take a cross-layer approach to bridge the gap between networking and communication. In terms of wireless networking, I find that physical layer information and capabilities can be useful in solving existing challenges and problems in wireless. And as I was doing this research, I also found it very interesting that the physical layer in wireless can be viewed as a sensor. And this sensing information can be used to build building blocks and concepts which can be used in applications in the application layer. And the localization project that we talked about is one such building block that we worked on. So in terms of future work, I feel that correlation can be a very strong primitive in terms of communication networking, and I would like to talk about why. If you think about wireless, in one direction you have signal in the physical layer, and the other direction you have decoded bits. If I say decoded bits, you will mostly probably think about data bits, but data communication also needs coordination, and hence we have a lot of control bits. Now, these control bits are an overhead, and hence we have seen a lot of protocols and research that have tried to reduce the overhead of the control bits. And correlation sits between signaling and decoding. It's neither signaling nor decoding, it's in the middle. And it gives us a cheap method of sending feedback or information in presence of data communication. So if you can take those control bits and move them from decoding to correlation, it might be possible for us to save bandwidth. And CSMSCN, or collision notification that I talked about today, is one such protocol in this domain. We have looked at how can you save energy by using correlation. And going ahead, I would like to ask the broad question, how do you redesign protocols using correlation as a primitive? Now, more broadly, I would like to augment sensing with wireless. So if you think about sensors on the phone, there are a lot of them, and if you take a multimodal approach, it's possible to create more opportunities and solve problems on phone as a platform. And we also see that whenever a new sensor gets added to this space, the opportunity space increases drastically. Now, apart from these sensors that we know, accelerometer, compass, gyroscope, there are these sensors which are also there on the phone, essentially the wireless physical layer. Now, these are the sensors which I believe has not been exploited a lot until now. So if you can combine this sensor space, I believe that the opportunity space will increase drastically, and we might be able to solve problems and come up with better opportunities in the mobile computing space at large. So at this point, I will conclude my talk. I would like to take any questions or comments.
Thank you.
time, I think we're going to take questions offline.
Sure.
And you're going to meet most of the people here. Okay, thanks.